Welcome and thanks for having us here in this nice summit. And my name is Ingo Boernig. I'm working in the field CTO organization of Red Hat. We are working with emerging technologies, new technologies that come up. And one of the projects we are working on and integrating now is something I'd like to talk about. And together with my colleague Christian.
Hi, I'm Christian. I'm a solution architect at Red Hat, and I work with German energy and utilities companies mainly and help them make use of open source software. So let me start by telling you something that you already know and have heard 800 times today. The traditional power grids are obviously evolving, so we're moving away from centralized power plants to something more complex, a decentralized system with numerous smaller renewable sources and prosumers and all the rest of it, which is challenging. And one of the challenges that we usually hear is that we're supposed to double grid capacity within the next 20 years, which is not easy to do. One of the things we need is obviously more secondary and primary equipment. And I'm getting there because this means that we will produce more data, and data is pretty useless unless you run some kind of algorithms or multiple algorithms on them all the time, which means you need compute, lots of compute, and preferably in the locations where the data is being produced. And that's where we are going to focus on in this talk. Now, to give you a little bit of an overview of the challenges that you will have with bringing basically IT to edge environments. Just to name a few, you're going to have to deal with security over long periods of time. You're going to have some kind of monitoring. You probably want to avoid vendor lock-in, and you want to make sure that whatever you invest money in isn't obsolete within the next 8 minutes of you investing in it. And at the same time, you don't want the speed of innovation to slow down, but you kind of want to change stuff all the time whilst keeping everything stable. So sounds pretty challenging to me. And on top of that, we're talking about a mindset shift, which means that people need to change their behavior, which is usually one of the most difficult things we can tackle. But to make it short, we're going to move from devices that provide specific functionalities to functionalities that need to run somewhere. And this little somewhere is usually some kind of IT platform, and this specific piece is in the center of today's talk.
Yeah, so that was the motivation, and now we are back to IT, so where we are comfortable talking a little bit about. And of course, we are doing that for a lot of industries and another people, and we have common challenges, and we see patterns here. And first of all, we look at limitations we have when we deal with things that are not distributed in the data center. Typically, we have limited resources, so compute resources. The hardware that we are using is really right-sized for the workload they are running on, and not so much for additional management overhead or other things that need to be run there, or that is defined later in the process. Also, the networks are completely different. They are not as redundant as in the data center typically, and the bandwidth is also typically limited. Also, the network connections are restricted. And a very, very important thing is, of course, we don't have IT staff that can really handle these things right beside your devices. So these devices need to be completely remote managed and need to work that directly from the start. Even the installation is something that has to be done by technicians that are not really knowledgeable about the technology. And of course, there are other restrictions and challenges. The other challenges are more risk-related and also about reliability and security. So what we need to do is when we distribute systems around the world and leave them there, we need to somehow control and monitor the configuration they have over time. And but that's not all, because the things are not static, because we are dealing with software. Software has bugs that needs to be, it's evolving and it needs to be updated. So updates need to be installed and work, but that needs to be very reliable. So updates, when update is failing, there must be something that brings the service very fast back on. Yeah, so that we need to deal about that. And finally, yeah, we need to control and analyze and keep track of all these software components that come from vendors and developers and keep them up to date. So we need to have an inventory of all the different components that are there, and then look at them and see, oh, we have here a component that is probably vulnerable to a certain vulnerability, and we need to patch that as soon as possible. Okay, coming back to Christian.
So quick question to you guys is, does that so far resonate with anyone? So who here in the room does deal with IT components and has to like work with these kind of problems? Do we have people in the room? Okay, perfect. Thanks, Daniel. So what would your day look like if you could manage thousands of devices anywhere in the world, potentially, by just describing what you want your world to look like and then having some kind of system make sure that this eventually happens? So our proposal is that this can work today, and at the end of the talk, I'm going to ask you again if you believe me or if you have any gaps that you see in our approach. So let's address the elephant in the room. We just heard about Ansible, and the obvious solution seems to be Ansible, right? However, Red Hat has been investing in Ansible for over 10 years now, and we can tell that at some point with tens of thousands of devices or VMs or whatever, plus there can be limits that are quite annoying. So just to give you a few examples of the shortfalls that you may experience, number one, you have to make sure that the Ansible controllers or the jump hosts have SSH or some kind of network connectivity to your nodes, which is something you might not want. Plus, whenever you run an Ansible job, it kind of like needs the target system to be available, which is not always the case, especially not in edge environments. So you end up hitting the deploy button a lot until stuff is eventually consistent. So we're looking at an alternative here, but that's not to say that Ansible is useless or it's a replacement for Ansible. It's more like a complement, I would say. So you're always going to have, say, network equipment or something else that you need to manage. This works quite well with Ansible, but on the individual application level or VM level or device level, we have something more interesting, which we called, I don't know who called it that, someone called it flight control. This came out of our emerging technologies team in the CTO office, and now we kind of like open sourced it and are looking for contributions. And the idea behind it is actually quite old. Don't get distracted by the exact architecture. What I want you to pay close attention to is the bottom right of the graphic, where it says agent. And you guys probably like, I thought we use Ansible to get rid of agents. Now we're back at agents. And that's true. And the reason we do this is because we don't need the central system to connect to all of the devices and establish SSH connections and manage whatever keys and all the rest of it. The agent calls home to a central system, asks what it's supposed to do, and then it eventually happens. So it's quite nice in that way. Which also, the second thing that I wanted you to pay attention to is the little arrow, which indicates exactly what I just said. Very, very simple. Now, unfortunately, some of you were in the session before and some weren't, so we're going to go a step back and talk about an enabling technology that we need to understand for all of this to make any sense whatsoever. So we're going to talk 5 more minutes about bootc and set the context here.
Yeah, so for those who have been in the talk before, you only heard about bootc, and this is really one of the enabling technologies we are making use of. And let's go quickly through the things what bootc is doing. So if we wanted to distribute systems with Linux on top of it, so if there are gazillions of methods to build images on Linux, nothing has really settled and standardized, and but there are several methods to do that, and it really depends typically on the platform where it has been deployed. So VMware has a different one than the Amazon cloud, and each hardware device maybe has another one. So we wanted to make that much easier and doing that. And if we look at a different approach, not at virtual machines or complete operating system images, but if we look in the world of containers, we already have this. Everything has converged on OCI images, yeah, that can be built and pushed into registries, shared and run everywhere. Yeah, so that's really something which works. Yeah, so in the Docker style where they have been invented, but that's not available for a complete operating system, at least not before 2 years ago when people started to do that. And that is what I wanted to show here with bootc is, yeah, it's possible. We can actually do that. And so by not inventing another image format, but just by adopting the image format that has been already standardized in the container world. And so we bring that together. We use the same tools, the same infrastructure, the same process, but we just stuff a kernel, a bootloader, and an init system into the container. That's a simple trick. And then we store it again in a container image. And then we can put this onto every device. And if you build container images, you can see it's really as easy. You can just build upon already existing images that contain these parts. So we do this here for the Fedora container, for instance. You can just take an existing bootc container, add stuff, and then you build your own. And then you can create individual images very easily. And there are bootc base images available for several distributions, for Fedora, for RHEL, for CentOS, but also for Debian and others. So it's really a universal method, this bootc, and you can create very easily new operating system images that can boot on devices. And one of these devices could be, for instance, cPath hypervisors for substations. Yeah, so you can use this image, and that was exactly what was shown in the talk before, and how to do that in a stable manner. But even there, you could even go further because it's a container image. You could also use the applications that run on top of them, of the hypervisor, and package them also as bootc, and they can be distributed. Vendors could release software as bootc containers, which can be pulled from registries and then started. So it's really a nice technology that, yeah, can be really transformational for doing this stuff. Good, but that was the enabling technology, bootc, that's where we build upon, but we are coming back to the original problem. We have not only one device, not 5 devices, not 10 devices, but 1,000, 10,000, 100,000 devices. And how do we do that? And how do we work with this? How do we onboard these systems completely remotely and secure? How do we take care that the deployed software on top of that is not tampered with, that we make sure that it's really its original state? And really, really important, how do we orchestrate updates without having any business interruptions? And what do we do when something goes wrong? It's not because it's IT, everything will go wrong eventually, so we need to have a plan B. Yeah, and I think Christian will tell us a little bit about that.
I'm the plan B. All right, so let's start from the very beginning of the life cycle. And by the way, when we say devices, it doesn't really have to be like a literal device. It can be, but you can think of VMs and whatever else, right? So let's start by the onboarding process. So the way the system, or both technologies, flight control and bootc, we just proposed together, basically give you an easy way to sorry. My Mac just broke. Hopefully not. To zero touch provisioning and zero, trust provisioning. So what this basically means is you have a system, you plug it in, and it basically puts the content on itself. And we'll get into how that looks like later. But the point on this specific slide is we support TPMs like hardware root of trust. Every device will have a client certificate. We can have signed operating system images and signed application images. And this is key because you can now make sure that from the factory to wherever you want it deployed, nothing was changed in between, right? So we're talking about software supply chain security, which is especially interesting when you don't have like physical access controls in your remote data centers or substations or whatever the case may be. So rogue devices get a big red X when they try to, connect to the system and be like, hey, give me all of your secured content. You just trust me. This doesn't work for the reasons I just outlined. And in practice, this means you don't need IT knowledge to deploy your edge systems, right? You need some person or maybe a drone that's able to take a device that's pre-baked with your content or image or whatever you want to call it, get it where it needs to go, plug it in, and then approve it and add it to the fleet. And what the fleet is will make sense in a minute. So you don't need you no longer need IT specialists to do that. And now the million-dollar question: will I be able to do a one-handed demo? You'll find out soon.
I can.
No, it's fine. I just want to flex on people. That's fine. So device management. Let's start with the initial approval that I just talked about. So just imagine we booted a new VM or a new system somewhere. What will happen is it will boot up in your image that you specified. It has a certificate in it, and it will talk to the management system and be like, hey, can you please approve me? And don't try to scan that QR code, by the way. It's cut off at the start. But this will bring you directly to the flight control UI, which is usually not black, but let's see. Okay, this looks like this. You can see, how many devices you have, the application status, the system update status, and many other things. But you'll also see that there's a new device that wants to be approved. And what the process will look like is you're going to look at the device and, for example, look at the specific boot ID or whatever unique characteristics you can think of. And then if let's say the on-site technician deems this secure and good to go, he or she will just click approve, give it a nice little name, in this case, Substation Dortmund, in an homage to Ingo, he's from there. And then he will click approve. And someone in the audience asked us about metadata before during the break. We collect a bunch of metadata about the devices, like the running operating system, architecture, kernel version, et cetera, et cetera. This is all collected from the agent. And without managing any SSH keys or any similar things, we have access to a terminal. And you can see here that this is indeed a black screen, but also a real Linux system, Fedora in this case. And we use bootc to do all that. So now we have a device in our fleet that basically does nothing other than report back to the system and be like, hey, I'm here. So what's next? What you usually see in, I think Ingo mentioned this before, is like you want to be on the left and have your fleet or your application to be at a specific version, but the reality is things are offline, things are unavailable, and over time it looks like a nightmare. With flight control, we have a concept called a fleet, which basically means a collection of systems that are supposed to look like exactly the same. Could be a substation, could be a retail store. And we do that by saying every device that has these labels attached to them, substation equals true, region, NRW, city Dortmund, is automatically part of this fleet and thus gets the configuration that we specify. And this looks like the following. On the left, we specify this box is supposed to have this operating system, this application, these configs, and bake it into an image. And every single device that is now part of the fleet eventually converges to this desired state. And now I need you to pay really close attention to this multi-million-dollar animation we put together for you. Eventually, the mess will turn into a nice converged fleet. You can clap if you want, but you don't have to. So, thank you. Are we good on time? We're good on time. What does it look like in the UI? And I need to do some yoga here. So as I said, we have a naked device that basically knows about nothing, and we're going to click on Fleet, and this is just our sample substation configuration. And as you can see here, we want every single device that was labeled with region NRW and the substation equals true to be part of this fleet and have this specific image applied called Fedora Substation. So what we're going to do is we go on our new device that we just deployed, and then we will give it 2 labels, the aforementioned ones. I'm going to click, see how quickly I can type. And then you can see it's already part of the fleet that we expect it to be in. And now the system will detect, oh, damn, I don't have this system running that I'm supposed to running, the image running. I'm out of date, so I'm going to boot into this new version. I'm going to reboot, and then everything's eventually nice and green. Perfect. So I'm going to skip through that. It makes sense if we see that on a slide in a minute. Okay. Right. So, and this is like, I want to double down on this point because this is one of the coolest things in this whole approach. Updating a system no longer means, running whatever, yum, DNF, apt-get, update, and then hoping for the best. The process is that the new image is downloaded onto the system, and then the update means that we boot into the new version, which means that there is no residue of old packages or configuration files. It's a complete clean cutover. And why is that cool? Because we can combine that with things like smart health checks. So I'm not sure about you, but I have heard many, many people tell me that they're afraid of updates and that they would rather not update stuff, because if they update a system that's 500 kilometers away, they cannot fix it when it's broken. But with this, now you can say, okay, what are the minimum baseline things that need to work in the new application, DNS, whatever, network connections, curl somewhere, whatever you can think of. And if this does not work, please automatically roll back into the latest healthy version. This is what we mean by zero touch as well. There's no manual intervention anymore. And now you could think, oh my God, Christian is absolutely insane. This means that if we change something on the fleet level, thousands of devices get updated at the same time, which is true unless you configure the rollout process. And without going into too much of a detail, you can think of it like specifying subsets of machines that you want to update at a time. For example, I don't know, just one machine per substation or whatever. You can control when the rollout should proceed. So for example, only when the previous device was updated successfully. You can be extremely creative to have full control over the the update waves. And then also you have something called disruption budgets, which means that you can control how much can go wrong until you completely stop the rollout. And this is also extremely flexible. What else should we mention? You don't have to configure or put the configuration of each device into each device manually, but there's a smart way to do that, if that makes any sense. So the system is built in the way that you can have all of your configurations for your devices, for example, in a Git repository, and then it will automatically understand based on the labels and the location perhaps, which configurations to apply. So in this case, if a given device is part of the Substations NRW Site 1 fleet, then it will automatically take the network configuration file that makes sense in this particular location. And then if you were to take this device and put it somewhere else, you would just in the software change the labels and it will automatically, apply the configuration that is reasonable or makes sense for that location. All right, quick last demo to show you what this looks like in real life. So we're going into the fleet configuration once again, and as you can see here, we have the device selector, and you can be extremely creative with that, right? You could create a fleet that only applies to, say, your beta substations or your beta locations or whatever, and then you could add a label that says canary equals true, and then you would control specific devices, give them the label canary equals true to add them to said fleet, and then you can use that as a precursor to your production rollout. So it's actually so flexible that I can think of a million examples and none of them make sense to you, so I'm going to leave it at that. So what else can you do? You can quickly and very easily configure specific files on the system on a fleet level, in this case a nice ASCII art that's supposed to read substations, but it kind of doesn't in this demo. So you can basically drop in files very easily, plus you can run or put applications on top of the existing systems, so you don't have to put your application into the base image. You can just say, okay, I want a Hello World application in Podman on these devices. And then you can add specifics about monitoring. All right, in the interest of time, I'm just going to quickly show you what I meant earlier. You can set rollout policies, disruption budgets, update policies. The only thing I want to mention here is that you can, and this is important if you have bandwidth constraints, you can say my devices should update or download the updates on day 1 at night or something, and then do the actual updates on a different day. So there's full control also over the scheduling of this. So, not going to click through that. All right. This is flight control in a nutshell, and Ingo is going to bring us home, hopefully.
Yeah, so thank you. So, and Christian promised that we wanted to have this vision in the end. So hopefully we could demonstrate that we are very close to have this. So to put that in another word, a device outside in the OT world feels like a container in a Kubernetes environment. You do the same. You just specify some kind of desired state. You can have everything in Git, and it eventually consistently evolves into that. So that's the design goal of this software. And the thing is, why did we do that? Because we have the requirement from many, many customers that they want to control a large number of similar remote deployments, and keeping the risk low and the security standards high at the same time, and have a method that is designed with simplicity and extensibility in mind. And that's why we created Flight Control. And Flight Control is free software. So it's developed in the open. We are looking also for contributors. Bring your ideas and make it better. There are also demos out there where you can look at it and try and play with it. And of course, as we are Red Hat, so we develop in the open, but of course we will offer also a Red Hat supported Red Hat Edge Manager that is built upon these flight control and looks exactly the same as we saw before. So we are at the end and quite close on time, so maybe a last question, or if you have in the room. Otherwise, we are still here. We are here, and we can meet in the during the breaks, and you can ask us questions.